Hey everyone, here we are, question 49, and I'm just gonna turn this way. Yeah, we'll dive into this fairly quick. We've done something like this in class, but we'll just review it, touch on a few pointers, and yeah, that'll be it. So we first start off here. We see our system. So a gymnast holds an iron cross, and we spoke about that before. So it's where a gymnast would hold on to the rings like thus, and here's their feet, here's their head, and they just hold this position here, hanging suspended above the ground, right? Okay, so they're holding an iron cross. The rings are acting upward of a force of 250 newtons, which we see there. And then the shoulder adductor muscles, so really, if you recall, abduction is out and away, adduction is in and down. So we see here, oops, sorry. We see here the force of the muscle is acting, and that's the adductors, where you'd have like insertion and attachment points along that angle. And there, it's all maintaining a static equilibrium. So we know that all our forces and torques have to add up to be a net zero, because there's no motion. If their arm has a mass of 7 kilos, so it's just saying this point, which is the center of mass for the arm, is 7, could be considered 7 kilo distributed across there. How much force is needed to maintain the hold? So really what we're looking at is, what is the force of the adductor muscles? In this case, primarily the lats, but the force of the muscles involved in this action to keep the person up in the air holding an iron cross. Okay, so to situate ourselves in this, where we can pull, you know what, maybe I'll just try to do it on here. So again, we have our axis point here right at the center in the shoulder joint, and we have our moment arm, or the radial arm, that reaches out from there. So and we have, when we're dealing with torques, and we can see this and know as soon as there's an axis point, we're not gonna necessarily initially think of linear forces. We're thinking angular forces. Of course, that when that's happening around a axis with a axis or moment arm, so we're going to be talking about torques, right? So to situate ourselves, we're essentially going to find all of our torques that are in a clockwise manner, and we know those torque, because there's nothing moving, is going to equal the counterclockwise, right? So any torques that are acting around the axis that way, that's of course clockwise, and any of the forces acting that way are counterclockwise. Okay, so we'll just assess our forces here. Well, we have one that we can see here. So we have our force of our muscle, and when we're dealing with torques, again, the big, most important one is whatever's acting as most perpendicular to our moment arm. So really, we're looking for a force ultimately, or force component, that's going to be there. Okay, so downwards, and so we can say, yep, that's counterclockwise. So if we're kind of making like a tug of war, we can say the force of the muscle is on the counterclockwise side. Okay. Okay, well, let's see what else. Well, we got this blue force up here. It's upward, or if we follow our arrow coming up and around, as it would pivot around that axis point, we're going to say that's clockwise. So we know over here we have our 250 newtons working upward. Okay, good. Just going to scooch that over a bit, give us a little more working room. Okay, so here we go. This is where we're at. And then we can also look at what other forces. Well, we also see this one. We got our center of mass of our arm, and that weight is going to pull the arm downward this way. Okay, So we also know somewhere in there we have some force that's acting downward in the same direction of the muscle. So I was just going to say the force of the arm for now. We can figure that out in a moment. And let's just double check to make sure that's all of the torques that we need to account for. So here's one force, yep. There's a second one, and here's a third one. Any others acting on the system? Nope, 3, and we have 3. So that's great, okay. Sorry, I'm just gonna go back a bit here. No, okay. So this is the system as we have it defined now. So let's just fill this out with a bit more detail, okay, and be a bit more specific. So when we're talking about torques, if we get our torque equation up, we kind of have 2, right? So there's one where we can say the torque is equal to whatever force we have that's perpendicular to the radial arm, right? But if we know it's not perfectly 90 degrees, well, then we have another torque equation where we have our force times the radial arm, but sine the theta, right? And anytime we get the sine out, we're really looking at y-axes or verticals typically, and cosine would be horizontal. But the reason, again, that we don't look at any horizontal components or parts that add up to this resultant force is any 0 or 180 degree forces act horizontally, and that's just along directly into the axis of the door. And so again, or into the shoulder joint. So again, if you think of this as a door, if you push directly down the door in the frame towards the hinge, it's not going to go anywhere, right? It's a direct force, so it doesn't move. So that kind of makes sense. Or if you just pull straight out on the door, it doesn't have any angular torque or any angular motion, right? So we're not really interested in that. So that's why we use sine there, right? Just as a reminder. Okay, so again, we kind of see that we're missing a little something here on our clockwise side. So yeah, we have the 250 newtons, but what we didn't include was this part, right? So again, if we look at this, we see that torque, or sorry, we can just write it out. So we can see that we have our force, so that's 250 times our radial arm. So this is centimeters, so you go 1, 2, and then that's into meters. So we got 1 meter out. Oh my goodness, sorry everyone, I'm just gonna redo that. Okay, so 250 newtons times the 1 meter. And again, if you just forgot where that came from, we're essentially replacing this torque with a counterclockwise torque, which was part of this force, which we could write torque equals Fr perpendicular, which is this here. So we have this force that's acting perpendicular, and so this is the R, or the length. I think in your answer key I put L, so it's length, which is similar to R, which is the moment R. So, but it's essentially just talking about the distance out from where the force is applied relative to where the axis of rotation is from. Okay. So that's all our counterclockwise forces. Of course, we have our force of the muscle, which again, it's always good to go back and be like, what am I trying to do? Right. Well, I'm ultimately just trying to figure out, what is that force? What is this force that is allowing me to counteract the up pull, right? And how much of this do I need? How much force is needed? And that's, again, coming from the muscles. So I don't know that, so that's there, but I do know that I might not know the force, but I definitely also need to know what the moment arm is for that. So I can put R there just for now. And because that force is occurring at an angle of 50 degrees, I also need to figure out sine theta, right? Because it's not perpendicular. Okay, so because we know those numbers, let's actually just put them in now. So instead of our R value for this, or what we're going to see is right here. So from the center of the axis to where the force is applied, and I'll clean that up in a second. Okay, so what are we looking at? 6 centimeters, so we move 1, 2 over, so that's 0.06 meters, okay, for our distance on that one. And then sine of theta, well, we know it's not really theta, we're actually trying to find 50. Okay, there we go. All right, and then last but not least, here we go. We have the force of the arm. Well, is this a force? Well, we're really just talking about the weight of the arm. And the weight of the arm is, of course, its mass, which we said is 7 kilograms, times gravity, which is 9.81 meters per second squared. Okay, so now that we have all this, we can start simplifying and moving numbers over. So, yeah, let's see. So this value, I feel like I forgot some. Oh, yes. Okay. So here we forgot the radial arm. Okay. So this is 0.4 meters. Okay. Because again, instead of just having we have our perpendicular action on the torque here, just to show you. Instead of our force, we have a weight, and then we still need an R in there, right? Because we're talking about torque. So, and again, it's 90 degrees, so we don't need that. So, because sine of 90 is 1. So yeah, that becomes mg R if we were to write that out in full. And of course, there's our M, G, and R. Okay, let's clean that all up a bit. Okay, sure. I can rewrite those if we need, but let's move forward with our calculation and shuffling things around. Okay, so perhaps one of the easiest things, or some of the things we're going to do, is we can calculate what's in the brackets here, simplify those, and then move them over to the other side. Okay, so we can start going through that process. I calculated it slightly different here in front of me, and I'll go through this other time, but if the numbers don't exactly line up with what you're seeing, it's probably just a bit of a funny transform calculation. So here in the purple, let's see, when I calculated it out, that would align with 27 point, let's say 5 newtons. Okay. And so what I want to do with that value, because it's addition here on this side, to move it over, I actually want to subtract that amount from both sides. So just to rewrite this, start getting it a little bit neater here. Oh, sorry, we can simplify that just to 250 Newton meters. Okay, and again, we're going to bring that value over here. So now that's going to be minus 27.5 newtons. Okay, it's going to be equal F muscle times 0.06 meters times sine 50. Okay, and let's see, when I calculate that value out, what I end up getting is 0.0459. Cancel that out. And I divide that by both sides to move it over to this side. 0.0459. Right, okay. So and just to be really clear, when I calculated these two numbers, this is the value I got. And so it'd still look like this, F muscle times this value, right? And so to move this over to the other side, I, of course, divide that because this is multiplied together. So I divide that, both sides, there we go. And just to make it look a little cleaner, do this equals the force of the muscle. Okay, and here we are. After all of that kind of song and dance, here we go. We're at the big show. Yeah, and so when we calculate this value out, what we end up getting is 4,848.8 newtons equals the force of the muscle. And of course, when we're just double checking how much force is needed, we're talking about the muscles being maintained here, and that's how many newtons. Okay, so just as a quick review too, you know, if there's quite a bit of force being produced, and so that might seem a little odd, as like a whole magnitude larger than what's going on here as far as trying to hold down. So the rings, I like what it's saying is the rings are essentially pulling upward on the hand, and these forces over here, you know, to hold that position, are trying to hold the body up, right? Yeah, so sorry, I was just trying to remind you of the context of the question here. So when it's saying the force of the muscle is almost 5,000 newtons, you know, it's really saying that that's how hard it's working to help maintain, counteract this 250 newtons on that side. Now, why is that? Well, why the big difference? Well, again, if you remember, a lot of joints in the body, so for example, in particular the shoulder joint, is a third class lever, right? And the way those look is you have some fulcrum, right? So you have a fulcrum, right? And then you have, say, like a force getting pulled, so force applied, and then you have some sort of like a load, so load applied, let's say. And because the force arm is shorter than the lever arm, the mechanical advantage is not there, right? Is this true throughout all of the entire body for every joint and muscle system? No, definitely not. And I think one of the best examples of where we would see something where our mechanical advantage is closer to 1, so that means the ratio between or just the amount of, let's say, force applied relative to the sorry, I just want to do this. Just do it this way. Oh, sorry. Usually we want the force applied a lot less than the load applied, and that would be a mechanical advantage. So the closer this gets to 1 is actually with a first class lever system, more or less, where in our jaw is called the masseter muscle. So the force and the fulcrum in our jaw, as well as where the muscles pull to close our jaw shut. So if this is our teeth, so our molars, sorry, this is the rest of the skull, kind of off this way. So our molars back here actually have almost a direct load application to where the muscle is being applied. And so you get a ratio of 1, because this the length of the force arms is essentially 0. Okay, but anyway, again, the chance that or the percentage of joints that we have in our body that are set up that way are significantly less. In particular, our limbs. And so when we're talking about sport and biomechanics, we really want third-class levers for our limb system. Again, the biggest reason is, yes, the force here, where we're applying our force, needs to be significantly much, much, much greater than what our load is, right? If it's our arm or like a baseball bat or an implement. But the trade-off for that is speed, right? Much, much quicker movement for this point. The velocity is much greater out here than here, relatively speaking. So we get more speed or more velocity at the end of our limbs. Okay, that was a bit of a review of levers as well as torque and how to sum different forces on different systems. Okay. Yeah, hopefully that was helpful if you didn't catch it on the first time through in class. Again, took a slightly different approach here, I believe, from what we did in class. So I've been able to see it a couple of different ways now.